Hello, everyone. My name is Timur, and some of you are new here. And let me introduce myself, probably. So, I'm working in the industry of programming and education for probably almost 30 years. And now our goal here with this AI school is to learn some new techniques, some new advanced methods on how to work with AI. And I don't know, have you seen the task or not yet? But let's discuss anyways what we need to do right now. So hopefully everyone is familiar with what an AI is and what Python is and capable of programming and all this some trivial stuff. Okay, so today we're going to talk on agentic orchestration. That's a very serious task. When you're working on uh, AI native AI native um, applications, AI native companies, whatever, your goal number one is to make your agents friends. So you need to orchestrate AI agents somehow, and that's one of the main problems. And many people start working on this, not even thinking about how it's going to be. Uh, Mostly people simply discuss this with Cloud Code and say we need to build this and this application, and they don't care about how these agents are going to communicate. And in most of the cases, there is even just one agent, AI agent, when you could build several agents that could work simultaneously and perform much, much better. So uh, agentic orchestration. Let's talk about this. Yeah, I just told you that we have several AI agents, and that can be that they working on different tasks. They can work with different models. Maybe some agent is working with Opus or Sonnet, when the others work with some very tiny models like Gemma, and they somehow need to communicate, and so they can be split by task, by effort, by context, by skills, whatever. So, and your goal is to make them communicate effectively. Uh, so I think, well, at least if you already tried to build any kind of AI applications, you already are familiar with this kind of problem. So hopefully there is no need to really explain on the motivation. And let's talk on these four approaches. There are many more approaches, but these are most common. So we have a sequential one. This is a deterministic pipeline, and people also call it a flow. If So this is a flow. When you have some steps and you know that you need to execute something step by step, and then in this case, it's not a big problem to communicate because you just know that the input of the second agent is the output of the first one. Then we have a centralized one. This pattern assumes that there is a supervisor or some router that directs traffic and gives tasks to some sub-agents that you already probably heard that of this definition. So we have the main agent, which is like a supervisor, and it can call sub-agents. People say it's like swarm of agents, whatever, and you can call it one by one. You can call them in parallel. If you have, I don't know, 50 documents, and you need to process each of these documents, they are independent. Why not do it like in parallel. And in this case, that would be sub-agents. Uh, let me write the sub-agents here. Shared state is when we have some context, we have some, let's say, blackboard or state that can be just one document, a series of documents that can be a report, that can be software that's developed right now. So here, let's write Claude. That's how. Actually, this is not true. This is partially true. So Claude is using the centralized and the shared state, both patterns. So let me write Claude here too. So the state here is the software. If we are talking about the Claude code, yeah, that code is the Claude code makes more sense. If we're talking about Claude code, then this directory, the folder where you are working on this software is our shared state. And the agents may work on this state, on this document, this project. They can work simultaneously, step by step. There may be two agents that are working on the same file. They will conflict. So in most of cases, shared state does not assume parallel work of agents, but it's also possible in some cases. An event mesh. This is a complete autonomous agent-to-agent protocol. This is it's event sourcing. Event sourcing is when you have a journal. You have a journal where all agents write something, and some well, normally every agent is triggered by some events, and they emit some events to this journal. This is called event sourcing. If we have time, we may discuss this more because this is the most complex one. So this is event sourcing. That's what people call it. We have an event mesh. So we have some journal in the middle, and we have several agents, and they're working with this journal. These agents they do not communicate with each other at all. They don't know about their existence at all, so they don't care. What they have is they know that they need to be triggered on some event. They need to do some job, and all data that's needed to fulfill the job should be in the journal. Okay, we will discuss this later. So, Mm. so pattern one, sequential pipeline. Let's discuss on example of when you use this one. So let's say you are building you're building lawyer system. So you give some contract, and you need to process this contract. And at the end, you should say whether to sign this contract or not. Maybe you need to add something to it. Maybe you say no, we reject it, or we accept it. What we do is we have several agents, but they're working one by one. The first agent is parsing our contract. It can be a scanned version, it can be a beautiful PDF file. So it parses this contract and produces either a text an MD file, or it can produce a lot of chunks for a rack pipeline. So it may split it somehow by context into a lot of documents, and then the next agent will know that there is some database that it can work with. And then the second, so the first one is parsing. The second agent now knows that the document is parsed. It goes through this document. It's already a very convenient one, some markdown file, let's say, and it collects some data. So it checks the ID of the counterparty, the name of the counterparty. It checks the amount. It checks whatever the context and like what this contract is about. It summarizes the contract, and then it saves all this data. That's the main data. It saves somewhere, and then the Agent 3 is has some integrations with government systems, and it goes and collects more data on the counterparty. It goes, so this is not an AI agent. It's a normal like agent that simply takes this task and say, okay, I will go and collect data about this company. So it goes by ID and by company name, whatever. It may browse the internet. It may go to governmental systems and collect data about this company, and so it knows whether this company has some tax debts. It knows how many people are working on this in this company. So if you are signing a contract on $1 million and there are only 5 people working in this company, that's a risk. So most probably it's a scam, whatever. There may be some problem later with this company. And it collects everything else about, let's say, the founder of the company. So it collects any kind of data. And then the next agent is taking all this data, and now it has full context about this, and it has some rules. So the rules are like, go and check how many people are working there. Does it somehow correspond to the amount? Go and check if the founder has any kind of problems with law, whatever. So there are some, I don't know, maybe 50 rules, and all these 50 rules are working in parallel. That's quite possible. It's still a flow. So we have one agent, second, then 3 agents are working simultaneously, then the fourth agent, and so on, so on, so on. So it goes and scans the contract and the rest of the data. It scans by some set of rules. Uh, the next step is a huge model, Opus, let's say. It collects all data. It collects what the previous agent has collected. It goes, it knows all the like RAC documents. It produces a report. Okay, so the last one, the most capable one, is producing the report, and then there may be another agent that converts this report to a PDF file, and then we get this report in a nice PDF saying, yes, this company is I don't know, is stable, whatever, so we can trust them, so you can go and sign this contract. So that's the flow. The pattern one. If you have questions, you may ask me, and otherwise we continue. The second pattern is a supervisor. The most obvious example for a supervisor is a help desk. So let's say there is a new ticket from your customer, and the supervisor knows, okay, so there is a bug in the system, and now it knows that, I don't know, some guy is responsible for this bug, or maybe a department. So it forwards this to another agent that is responsible for this task. And it knows, okay, we need to check this and this. Maybe we send an email. Maybe we fix this problem instantly. Maybe we reply, we say, this is not a bug, it's a feature, whatever. So it goes back to the supervisor, and then the supervisor replies to the customer saying, we cannot help you. Um, so, and again, Cloud Code or Gemini, whatever, Gemini is like Codex are also following this supervisor pattern, because there is one agent that is working with other sub-agents, and that's also Like there is some bigger model. So in the previous example, the bigger model only started working at the end. So when we collected data with the previous, like the smaller models, and the bigger model started working only at the end, uh, producing the report. Because it's the most capable, it knows much more about maybe laws, whatever. And in this case, supervisor starts to work and it controls the subagents and it controls the flow. It may stop an agent, it may start some several agents in parallel. So there are some questions. How universal are those patterns? Opus 4.8 and the cloud code behaves differently. How to verify patterns have statistically significant positive impact on outcomes. So again, in case of cloud code and codex, they both follow two patterns, like the supervisor and the next, the third one, and this shared context. So they have shared context, like Cloud Cowork. It also has several agents working, and they have the shared context. You probably cannot verify the patterns that have some impact, or because this can only be like you can only find this out experimentally. Otherwise, this is not possible. And I wouldn't say that Opus 4.8 is behaving different from GPT 5.5. They have different set of rules. The main prompt, they have different models. That's the reason why they behave differently. But in general, they have the same pattern. That's 100%. Uh, Next question. We can create system of AI agents which are founded by RL and LLM. What is RL? And able to replicate human behavior in employees' duties, for example, financial department. That's what people want to do. They believe they can do it. But especially with financial department, the thing is that we still need this so-called human in the loop. When human is responsible for the output of LLMs, so the human is responsible for everything. So LLMs are never responsible for this, and that's the biggest question when we are replacing uh, human with AIs. Human still should be there to take the responsibility to check the AI output and say, okay, this is correct, this is not. Even for emails, okay, if AI is 100% sure what to reply, maybe it can do it automatically. But in general, normally humans should reply. Or, of course, if we know that we are talking to a bot, we know that we are like writing an email to a bot, the bot can reply the email stating that this is a bot reply and this is what it thinks the correct answer is, but there is no responsibility for this. So if we're talking about financial department, we cannot rely on AIs completely. So anyway, we need to uh, we need to somehow have a human there. In general, yes, you can replace human behavior, but you need to track it, and for this, you probably need a journal. That's the last the last pattern. So we need a journal of each step taken by a human. If it's working, if it's, I mean, the human, they are working on the computer, so we need to record the screen. If the only thing it produces is emails, then we need to record emails and so on. And then we can probably teach AI and replace a human. But again, this is the dream of all CEOs, but currently this is not really possible. Could you please explain the main goal of the course? So formally, what artifact we will have at the end of the course? Okay, we will at the end of this lesson, let's say, we will have a task, and at some point, the goal of the course is to learn how to orchestrate, to learn how to build complex AI systems, so we can replace human. That's our goal probably. Uh, you can build any kind of product. You may ask me any kind of questions while you're building it. We will be working on some specific problem, namely teach trying to teach our users uh, any topic. So we want to replace courses by uh, providing small daily lessons. So we keep the human whom we want to replace. We want to keep the human up to date with any kind of topic, AI, finances, whatever. So that's what we are going to build. In parallel, you may build whatever you want, and we can also discuss this. No problem. Um, so that was pattern two, supervisor, shared context. I think we have already covered this. Let's talk about the fourth um, pattern, and that's the most complex one. And normally, this pattern is used when we are working with finances. And let's say we have trading bot, and for this system, we will most probably need event sourcing. Why? Because we need to react on events, and this is not only the news we have to react. So it's not like Elon Musk said Bitcoin is not eligible anymore, and then Bitcoin goes down. Not only things like this, because this is not the event we are talking about. The events here are more like what system is producing itself. So system, I mean several agents, several microservices. They produce some work, they produce some output, and write, they report every step of what they do to this journal. Uh, let's say we have a bot. So we have 5 to 10 bots uh, trading some of them Bitcoin, some of them Ethereum, whatever, and they get they get data. Maybe they get signals from some other agent, and they know they need to sell Bitcoins. So what they do is these bots, they don't directly trade. What they do is they say it would be good to sell 2 Bitcoins today. So it produces a command to the like trading mechanism saying uh, sell 2 Bitcoins. And then the other system is reacting on this event, which is really trading. I mean, no, sorry. The first like accounting system is checking, does this bot have enough assets to trade 2 Bitcoins? It may say no, reject. It may say yes, approve. If it's approved, the other bot, uh, it's not AI bot, it's a deterministic one, gets the data. It says, okay, we need to trade 2 Bitcoins. So it goes to market, goes to API and really trades it 2 Bitcoins. And then it reports back and say, okay, I have traded 2 Bitcoins. And the previous one, the accounting says, okay, now we subtract 2 Bitcoins from bot assets, but we add USDT to this bot, so it can now purchase something else, but we cannot sell any Bitcoins because like zero is left. Okay, and all these mechanisms, all these microservices, they can be AI agents, they can be deterministic services. They're working in parallel. They don't know each other at all. They don't know about the existence of others at all. And that's the most like beautiful model in sense of stability. So we know that the bug in one system is not causing any problems to the other systems. And also, a very good model when you are working with Cloud Code, Codex, because you know that all these AIs, like they have some limited context, and in case of event sourcing, these agents, they only need to know what this themselves what they need to do. That's a crucial point because they don't care about where these events come from, and they don't care about how and how and by whom. Nobody cares about this, so it has some goals. It works with these goals, uh, saying when this event occurs, we need to do this and this and these steps, and then emit another event, maybe an error, maybe a successful event, maybe emit a command to some other agent. We don't care about the other agent at all. So we don't need to know how it works. So the context for the AI, like Cloud Code, is very limited, and it works with this context much better. Okay, so in this sense, event sourcing is very good, like in our modern world, just because of this. So it doesn't need to hold the complete project in its context, because like even though, let's say, Opus 4.8 has a million token context, uh, it hallucinates a lot, you know, when we really use a lot of context. If we are using more than like 128K, it already produces some problems. So don't be flattered by this 1 million context, because it's not that effective. The recent events in this context are like they have higher priority, and the earliest have much lower priority. So don't use 1 million context. Never. I would not recommend this. Try to keep it small. Let's talk about the task. Let's try to build 3 agents, very simple ones. And the pattern you want to use is up to you. And uh, it can be a mix of 2 patterns. It may be uh, some other pattern or whatever. So, but the goal is to make 3 agents work somehow. They need to somehow communicate. They have to work together on the same data, and we need to orchestrate this. Okay, this is up to you what you use. Um, I think all of the patterns that we discussed today can be used. So I want to see how you implement it, and I want to see which one you choose. And then next time we can discuss which one is better, what uh, advantages and disadvantages each of the patterns have, and which one would probably I choose out of this. So the first agent is fed a URL. How this is going to be? It may be a console Python application. So you say, I want to get data from this Medium page, and it goes fetches this data, this Medium page, uh, says, okay, this can be a lecture, so maybe a set of lectures, and it can say accept or reject. It may reject completely, saying this is not going to teach anything. Otherwise, it can produce several lessons, and it can give this data that was already structured and text data. It can give to the agent number 2. And what it does is it produces a set of lessons saying we are working on AI and we need to give this and this and this topics. And these are the lessons we want to produce. And then the third agent, knowing the users in our system. So we have this users MD here. So it reads all data about users, like not only first name and last name, it can see all the profile, what they're working on, and what their interests, and whether like they like humor or not, whatever. And based on the users, based on the topics, it produces a personalized lessons. That's it. Okay, very simple flow, and try to implement this flow, and try to see whether you are happy with it, whether it is performant or not, and whether you like it or not. Maybe it became too complex and you would like to not use this pattern, though you have already used it, you have implemented it, and then you say, okay, I didn't like it because it's too complex to debug, maybe to, or maybe you like it. I don't know. Up to you. Okay. That's it. Do you have any questions on the task?